When I say something like, consider a simple quantum system, I don't mean simply ignore all the details about that system, ignore all its extra structure and all the extra things it can do. What I also mean is ignore everything else in the universe. The extent to which this is possible essentially tells us how effective the reductionist approach is going to be to try and understand the world around us. If we really need to know the detail of a very large number of systems in order to understand what's going to happen, then in some sense we're set up to fail. We can't necessarily handle that level of complexity. So whenever we reduce something down to a system, we are making some assumptions about the functionality of the dynamics of that system. We're assuming that it's possible for that system to be sufficiently isolated in ways that matter from everything else in the universe that we can consider it by itself and draw some useful, meaningful conclusions from that. So for example, if I say, consider a two-level atom, an atom sitting there in space with two important electronic levels. The first thing I'm doing is I'm knowing all the other electronic levels, which for some reason don't come into it. Perhaps it's in some excited level and there's only one thing it can decay down into. And so all the excited ones, there's no energy for it to jump up there, so they never come into our description of the system. Furthermore, I'm saying ignore the tree in the garden next door to that atom. Ignore the houses, ignore the rest of the cosmos. So that all comes into everything else. So when we describe a quantum system, we often get that very reductionist view. But also sometimes we need to think about its interaction with the universe a little bit. So take that two-level atom once again. Sometimes it interacts with the rest of the universe weakly. Perhaps it might emit a photon. Perhaps it might be in an excited state, and it might emit a photon and go down to the ground state. The photons are part of everything else. So in fact, this system is coupled to everything else in some way. So the system and its environment might be weakly coupled. But there might be some useful way in which we can just say, let's look at that two-level atom, let's look at that simple quantum system and describe how it behaves. Now quantum mechanically we know that if we have the state of a system and the state of everything else, then the total state is just the tensor product of those two things. So our system and our environment. But if there is some weak interaction, we might find that our system starts to get a little bit entangled with our environment. Now, are there any sensible things we can say about a system in that situation? The answer is yes, but we have to expand our idea of the state of a system to include classical uncertainty. If for this system I have one state psi1, and I give that to you half the time, the other half of the time I give you a different state psi2, then there's no way to actually write that state down in quantum mechanics. Obviously, I can add them together, and if these two states are orthogonal, then you could say that you have one of them half the time and the other one half the time. If you make a measurement, that would be true. On the other hand, there is still physical significance to this plus here. Okay, so that plus means something. It might be a minus, or it might be a plus I, or any other kind of phase, and that would have different physical consequences. So in some sense, in order to have classical uncertainty, we need a new method of writing it down. We could say that we have the state psi j with some probability pj, and that covers all the possibilities we might have, but it's quite a clumsy way of writing it down because this list might be very long, or it might even be uncountably long. It might be infinite. And so what we're going to do is we're going to write down something of this form with an operator called a density operator, or in finite dimensional systems is often called a density matrix. Now a density operator, as the name suggests, is indeed an operator on the Hilbert space, and so if the Hilbert space has dimension n, then this thing has dimension n squared, so that's quite a penalty we've just paid. On the plus side, it turns out that things of this form can handle lists of arbitrary length, so you can have as many items in your list of probable states as you like, and you'll never need to describe something bigger than this operator. When we made this list up here, if you have these states, there's no particular reason and no requirement for these states to be orthogonal to each other. So you could have one state with probability 50% and another state with probability 50% that wasn't orthogonal to it. And as you might expect, that means that there are different lists of these things that give you the same density operator, but only things with the same density operator that act the same on different measurements. So this description up here is actually not unique, whereas this thing down here is. Now to describe the outcome of an arbitrary experiment you might do on this system, it turns out all you need to know is the expectation value of an arbitrary observable. That might seem a little bit counterintuitive because the expectation value of an observable only gives you the average of that measurement. But remember, if we know all possible expectation values, then we don't just know the expectation value of, say, A, we also know the expectation value of A squared and A cubed. and so on. And what that means is we can finally calculate the precise spectrum of possible measurements. So if these little a's are the eigenvalues of this observable, then all of these moments together give us the precise spectrum. So if we measure A, all the moments of A tell us exactly the probability of getting each answer. And so on for all other observables as well. So if we know the expectation value of every observable and every moment of every observable, then we know everything we need to know. So if we can calculate the expectation values from our density operator, then we're done. How do we do that? Well, supposing we have the expectation value of just a pure state, and a pure state has just probability of 100% of one thing. Then we know what that is. That's just this. Now, we'd only be able to calculate that if we actually did a lot of measurements on our state, psi j. So if we had psi j lots and lots of times, and we did lots and lots of measurements of A, eventually averaging out all those things would give us this expectation value here. However, we're not always going to get a particular psi j. Sometimes we're going to get different psi j's, and so that means the actual average is going to be a weighted sum. Now, what does this have to do with the density operator? Well, we can always insert a completeness relation here. So if we put in the identity operator into there, that shouldn't change anything. And remember, we can always expand any identity in terms of a complete orthonormal set of basis states, where these k's are our complete orthonormal set, and if it's a continuous set, that sum's just an integral, it doesn't matter. And now what we have is we can take, because all inner product's linear, we can take that sum out. And now, because these two things here are inner products, they're just complex numbers, which means that we can rearrange them at will. And again, because inner product's linear, we can move the sums around. And you see that this bit in the brackets is just the density operator, exactly as we defined it above. And on the outside, we have the sum over a complete orthonormal basis, and that's just called the trace. So if you want to find the expectation value of an arbitrary operator A, you just apply it to the density operator and take the trace.